In the dusty archives of ancient Mesopotamia, carved into clay tablets over 4,000 years old, lies a story that might chill you to your core. The Sumerians, those remarkable people who gave us the wheel, writing, and mathematics, spoke of Nibiru, the crossing planet, a wanderer from the deep cosmos that returns every few thousand years, bringing with it the power to reshape worlds. Now, you might think this sounds like primitive mythology, ancient fears projected onto the night sky. But here's what's unsettling. Some of the astronomical knowledge contained in these tablets is so precise that we've only recently been able to verify it ourselves. They knew about planets we didn't discover until the telescope was invented. They understood orbital mechanics that took us millennia to rediscover. So what if they knew something we're only now beginning to understand? What if there really is something massive lurking in the outer darkness of our solar system? Something that could fundamentally alter life as we know it? This isn't just ancient speculation anymore. In 2016, two respected Caltech astronomers published calculations suggesting that a planet roughly 10 times the mass of Earth is hiding in the frigid outer reaches of our solar system. They call it Planet 9 now, but the implications are the same as those ancient warnings about Nibiru. Something is out there, something big. And if it exists, it could change everything. Hash hash. The hunt for planet XTH, hunt for this mysterious world, didn't start with modern telescopes or computer simulations. It began over a century ago with a brilliant astronomer named Percival Lowell, who was convinced that mathematical irregularities in the orbits of Uranus and Neptune pointed to an undiscovered planet. Lowell called it Planet X. The unknown world dot in 1906. Lowell began his systematic search from his observatory in Arizona. He spent years photographing the same patches of sky, comparing images night after night, looking for the telltale movement that would betray a distant planet among the fixed stars. Lowell never found his Planet X. He died in 1916, still searching, still believing that something massive was pulling on the outer planets with its invisible gravitational hand, but Lowell's mathematical predictions weren't wrong. In 1930, a young astronomer named Clyde Tombaugh, working at Lowell's observatory, discovered a new world orbiting beyond Neptune. They named it Pluto, and for decades, astronomers thought this was Lowell's Planet X. The mystery was solved, except. It wasn't. Pluto turned out to be far too small to account for the orbital irregularities that Lowell had detected. This tiny, distant world, barely larger than our moon, couldn't possibly exert enough gravitational influence to perturb the orbits of massive planets like Neptune. The mathematical evidence that had driven Lowell's search was still there, still unexplained. Planet X remained hidden. For most of the 20th century, the search for Planet X became something of an astronomical curiosity. Better measurements of planetary masses seemed to reduce the orbital irregularities, and many scientists assumed the whole thing had been based on measurement errors. The idea of a massive, undiscovered planet in our solar system seemed to fade into the realm of fringe theories and conspiracy. Websites, But science has a way of resurrecting old mysteries with new evidence. In the past 2 decades, as our telescopes have grown more powerful and our understanding of the outer solar system has expanded, we've discovered something extraordinary. The region beyond Neptune isn't empty. It's filled with thousands of small, icy worlds, collectively known as trans-Neptunian objects. And these distant objects are behaving in ways that don't make sense, unless something massive is influencing their orbits. Hash hash. The mathematical breakthrough, came not from finding the planet itself, but from noticing what it left behind. Like a detective studying footprints in snow, astronomers Mike Brown and Constantine Bedigen at Caltech weren't looking directly for Planet X when they stumbled upon the evidence that would change everything. They were studying the strange behavior of objects at the very edge of our solar system, worlds so distant and cold that sunlight takes hours to reach them. What they found defied explanation. In the vast Kuiper belt beyond Neptune's orbit, small icy worlds were clustering together in patterns that shouldn't exist. Imagine throwing a handful of marbles randomly across a field, only to find them arranged in neat rows. That's essentially what Brown and Bedigen discovered in the outer solar system. The objects in question are called trans-Neptunian objects, or TNOs. These are the leftover building blocks from our solar system's formation, chunks of rock and ice that never quite made it into becoming planets. By all rights, they should be scattered chaotically throughout the Kuiper belt, their orbits randomized by billions of years of gravitational interactions and cosmic collisions. Instead, the most distant TNOs all have orbits that point in roughly the same direction. They're clustered together like sheep in a cosmic pasture, and the odds of this happening by chance are astronomically small. We're talking about a statistical probability of roughly 1 in 15,000. In scientific terms, that's compelling evidence that something is organizing these orbits. Brown, who had previously discovered several dwarf planets, including Eris, knew he was looking at something unprecedented. It was so striking that we couldn't ignore it, he would later recall. These objects are behaving as if they're being herded by something massive that we can't see, but identifying the problem was only the beginning. Brown teamed up with Bedigen, a theoretical astrophysicist who specialized in orbital mechanics, to figure out what could possibly cause such organized behavior in the outer solar system. They ran thousands of computer simulations, testing different scenarios, different masses, different orbital configurations. The answer that emerged from their calculations was both elegant and unsettling. A planet, not just any planet, but a massive world roughly 5 to 10 times the mass of Earth, orbiting the sun at an average distance of about 400 to 800 astronomical units. To put that in perspective, Earth orbits at 1 astronomical unit from the sun, and Pluto averages about 40. This hypothetical planet would be so far out that it would take between 10,000 and 20,000 years to complete a single orbit around our star dot. The gravitational influence of such a massive, distant world would act like an invisible hand, slowly but persistently tugging on the orbits of smaller objects over millions of years. Through a process called gravitational shepherding, Planet 9 would gradually organize the chaotic Kuiper belt into the neat patterns that Brown and Beattygen observed. Hash, hash. The fragile clockwork of space to understand how Planet X could potentially end all life. We need to step back and examine something most people take for granted. The delicate clockwork that keeps our solar system stable. You see, planetary orbits aren't fixed rails in space. They're dynamic, ever-changing relationships governed by gravity's invisible hand. And even tiny perturbations can cascade into cosmic catastrophe over millions of years. Think of our solar system as an intricate mobile hanging above a child's crib. Each planet is perfectly balanced, spinning in its designated orbit, maintaining the harmony that has allowed life to flourish on Earth for billions of years. But what happens when you add a massive new piece to that mobile? What happens when something 10 times the mass of Earth begins swinging through the outer reaches? Its gravitational influence rippling inward like waves in a cosmic pond? Our solar system has experienced this kind of gravitational chaos before. Around 4 billion years ago, during an epoch called the Late Heavy Bombardment, something triggered a massive reorganization of planetary orbits. The leading theory suggests that Jupiter and Saturn, our two largest planets, became locked in a gravitational resonance that destabilized the entire outer solar system. The result was catastrophic. Asteroids and comets were flung in all directions, many of them raining down on the inner planets in a bombardment that lasted hundreds of millions of years. The evidence for this ancient catastrophe is written across the surface of every rocky body in our solar system. The moon's heavily cratered face tells the story of those violent times. Mercury, Venus, Earth, and Mars all bear the scars of that primordial bombardment. On Earth, any geological evidence from that period has been erased by billions of years of weather and tectonic activity. But we can be certain our planet endured the same cosmic assault as its neighbors. This wasn't just a matter of a few extra shooting stars. The late heavy bombardment may have sterilized Earth's surface multiple times, boiling away early oceans and making life impossible until the bombardment finally subsided. Some scientists argue that life on Earth actually began after this period, suggesting that massive gravitational disruptions can quite literally reset the biological clock of an entire planet. Planet X, with its enormous mass and highly elliptical orbit, could trigger a similar reorganization. As it swings through the outer solar system every 10 to 20,000 years, its gravitational influence would perturb the orbits of countless objects. In the Kuiper belt and Oort cloud, these regions contain billions of icy bodies, potential comets just waiting for a gravitational nudge to send them careening toward the inner solar system. Hash, hash. The Oort cloud catastrophe. The Oort cloud, in particular, represents an enormous reservoir of potential impactors. This spherical shell of icy objects extends roughly halfway to the nearest star, containing perhaps 1 trillion comets in slow, stable orbits around the sun. Most of these objects will never threaten Earth under normal circumstances. They're too distant, too stable, too well behaved. But Planet X's passage could change all that. Computer simulations show that a massive planet passing through or near the Oort cloud could gravitationally scatter thousands of comets into new orbits. Some would be flung out of the solar system entirely, lost to interstellar space. Others would be nudged into elongated elliptical orbits that carry them into the inner solar system, where they could pose a direct threat to Earth. The timescales involved are both the most terrifying and most reassuring aspect of this scenario. Unlike the dramatic planetary disasters portrayed in science fiction movies, Planet X's influence would unfold over thousands or millions of years. The gravitational perturbations would slowly, inexorably alter the orbits of distant objects, building up like compound interest until the effects became impossible to ignore. This gradual nature is actually what makes the threat so insidious. By the time we noticed increased comet activity in the inner solar system, the cascade of orbital changes would already be well underway. We might have decades or centuries of warning before the peak bombardment, but stopping or deflecting thousands of incoming comets would present challenges far beyond our current technological capabilities. The astronomical record provides evidence that such bombardment periods have occurred throughout Earth's history. The fossil record shows several mass extinction events that correlate with increased impact rates. The extinction of the dinosaurs 66 million years ago, triggered by a massive asteroid impact, was just one of many such events. Some scientists have proposed that these extinction events follow a rough periodicity, occurring every 26 to 30 million years, suggesting a cosmic cause that regularly disturbs the solar system's stability. Signs hidden in plain sight. The universe has been trying to tell us something for decades. Scattered across the data archives of space missions, buried in the observations of veteran astronomers, and hidden as subtle movements of distant worlds are clues that something massive lurks in the outer darkness. Consider this. Our entire solar system is tilted. Not just slightly off kilter, but canted at a 6-degree angle relative to the sun's equator. For years, astronomers assumed this was simply a relic of the solar system's formation, some primordial accident frozen in cosmic time. But recent calculations suggest a different explanation. The gravitational influence of a massive, distant planet could slowly torque the entire solar system, tilting it like a spinning top that's been nudged off balance. The mathematics are elegant and unsettling. A planet with roughly 10 times Earth's mass, orbiting in a tilted elliptical path, could exert just enough gravitational leverage to explain our solar system's mysterious orientation. The process would take millions of years, imperceptibly slow by human standards, but inevitable as the tide. Then there are the spacecraft anomalies, those puzzling deviations from predicted trajectories that have plagued space missions for decades. The Pioneer spacecraft, humanity's first messengers to the outer solar system, experienced unexplained deceleration as they journeyed beyond the orbit of Saturn. The effect was tiny, just a few nanometers per second squared, but it was real and measurable and completely inconsistent with our understanding of solar system dynamics that the Voyager probes detected similar anomalies, along with unexpected variations in the solar wind and magnetic field strength that didn't match theoretical predictions. Mission controllers initially attributed these discrepancies to instrument errors or unmodeled forces like solar radiation pressure. But as more data accumulated, a pattern emerged. Multiple spacecraft launched years apart with different trajectories and instruments all detected subtle but consistent deviations from what our models said should happen in the outer solar system. More recently, astronomers have discovered objects in the outer solar system that simply shouldn't exist according to our current understanding. Take 2015 TG 387, nicknamed the Goblin, a small world with one of the most extreme orbits ever detected. Its closest approach to the Sun is still farther than Pluto's most distant point, and at its farthest, it ventures more than 2,000 times. Earth's distance from the Sun. Computer simulations show that the Goblin's orbit is most easily explained by gravitational shepherding from a massive, unseen planet. Without Planet X's influence, objects like the Goblin should either have been ejected from the solar system entirely or captured into more conventional orbits. Instead, they occupy a gravitational sweet spot, stabilized by the very planet we're searching for, ##. The mathematics of extinction when astronomers model the potential interactions between Planet X and our solar system, they're not just calculating abstract trajectories. They're mapping the pathways to possible extinction, charting how a world 10 times more massive than Earth could orchestrate the end of life as we know it. Let's start with the most immediate threat, the comet storms that could emerge from Planet X's gravitational influence on the Earth. Cloud. Computer simulations run by planetary scientists show that a massive planet passing through or near the Oort cloud could gravitationally scatter thousands of comets into new trajectories. The process wouldn't be sudden, dramatic collapse, but rather a gradual erosion of orbital stability that unfolds over thousands of years. Picture it this way. Imagine Planet X as a massive bowling ball rolling through a carefully arranged display of ping-pong balls. Each gravitational encounter nudges a comet slightly, altering its orbit by tiny amounts that compound over time. Some comets would be flung outward, lost to interstellar space forever. Others would be nudged inward, their orbits shrinking until they begin periodic visits to the inner solar system. The result, according to these models, would be a dramatic increase in comet activity throughout the solar system. Instead of the handful of bright comets we see each decade, Earth's skies could be filled with dozens of these icy visitors simultaneously. Most would pose no direct threat, passing harmlessly through the outer solar system. But in a population of thousands of perturbed comets, statistical inevitability suggests that some would be aimed directly at Earth. The geological record provides sobering evidence of what such bombardment periods can accomplish. The Chicxulub impact that ended the reign of the dinosaurs 66 million years ago was caused by an object only, about 10 kilometers across. The explosion released energy equivalent to billions of nuclear weapons, triggering global wildfires, massive tsunamis, and a nuclear winter that lasted for years. Complex ecosystems collapsed, and three-quarters of all species went extinct. Now, imagine not one such impact, but dozens or hundreds spread across thousands of years. Each impact would reset the recovery process, preventing ecosystems from stabilizing between catastrophes. The cumulative effect would be far worse than any single impact, no matter how large. Life on Earth has survived individual catastrophes before, but sustained bombardment could push our planet past biological tipping points from which recovery might be impossible, but Planet X's influence wouldn't be limited to comet impacts. The gravitational effects of such a massive world could disrupt the delicate orbital balance that has kept our solar system stable for billions of years. Consider the asteroid belt between Mars and Jupiter, a region containing thousands of rocky objects that are currently held in stable orbits by Jupiter's gravitational shepherding dot. Jupiter acts as our solar system's guardian, using its massive gravity to sweep up dangerous objects and stabilize the orbits of potentially hazardous asteroids. But this protective influence depends on the precise orbital relationships that have evolved over billions of years. Planet X's gravity could disrupt these relationships, destabilizing asteroid orbits and sending rocky projectiles toward the inner planets. The climate connection. Planet X's gravitational influence could also affect Earth's orbit directly, altering the delicate cycles that regulate our planet's climate over long time periods. Earth's orbital eccentricity, axial tilt, and precession cycle are all influenced by gravitational interactions with other planets, particularly Jupiter and Saturn. These Milankovitch cycles drive the natural ice ages that have shaped Earth's climate for millions of years. A massive planet like Planet X, even at great distances, could potentially amplify or disrupt these natural cycles. Computer models suggest that Planet X's gravity could gradually increase Earth's orbital eccentricity, making our planet's orbit more elliptical over millions of years. This would increase the difference between Earth's closest and farthest approaches to the Sun, potentially triggering more extreme seasonal variations and more severe ice ages. Alternatively, Planet X could affect Earth's axial tilt, the angle at which our planet rotates relative to its orbital plane. Small changes in axial tilt can have dramatic climate consequences. If Planet X's gravity gradually increased Earth's tilt, polar regions would receive more direct sunlight during summer, potentially triggering massive ice sheet melting and catastrophic sea level rise. If the tilt decreased, Earth could enter a permanent ice age as polar regions became permanently frozen in ice. Sheets advanced toward the equator. Recent research has identified potential evidence of such orbital disruptions in Earth's geological past. Some mass extinction events appear to correlate with periods of unusual climate instability that can't be explained by known factors like volcanism or solar variations. These mysterious climate disruptions might be signatures of previous encounters with Planet X or similar massive objects passing through. the outer solar system. Hashtag the hunt continues in the pre-dawn darkness of Mauna Kea, Hawaii. The Subaru telescope begins another night of patient humming. Its massive mirror, polished to perfection, gathers ancient photons that have traveled for hours across the void from the outer reaches of our solar system. Somewhere in that darkness, beyond the orbit of Neptune, astronomers believe a world 10 times more massive than Earth is slowly making its way around our sun. The search for Planet 9 has evolved into one of the most intensive astronomical campaigns in history. Multiple observatories across the globe have dedicated hundreds of nights to systematically photographing vast regions of the sky, looking for the telltale movement that would betray a distant planet. Among the fixed stars, Dr. Mike Brown describes the search as looking for a needle in a haystack, the size of the entire sky, but it's worse than that analogy suggests. The needle is moving almost imperceptibly slowly, and it's so faint that it might be invisible to current telescopes if it happens to be near the most distant part of its orbit. The Subaru telescope's Hyper-Supram cam can photograph an area of sky equivalent to 9 full moons in a single image. Each image contains roughly 900 million pixels, and a typical night of Planet 9 hunting generates terabytes of data. Sophisticated algorithms sift through these images, looking for objects that move with the characteristic speed of a distant planet. The computational challenges are staggering. The camera detects millions of objects in each image: stars, galaxies, asteroids, cosmic ray hits, instrumental artifacts. Distinguishing a potentially real planet from this cosmic background requires multiple observations taken weeks or months apart. Then careful analysis to confirm that a suspicious moving object has the orbital characteristics consistent with a massive, distant planet. Perhaps the most ambitious planet hunting project is the Rubin Observatory, currently under construction in Chile. This revolutionary facility will photograph the entire visible southern sky every few nights for 10 years, creating an unprecedented time-lapse movie of the cosmos. With its 3.2 gigapixel camera and 8.4 meter mirror, Rubin Observatory will be sensitive enough to detect Planet 9 if it's brighter than about 25th magnitude, roughly 10 million times fainter than the faintest stars visible to the naked eye. Citizen science projects like Backyard Worlds, Planet 9 have enlisted thousands of volunteers to examine astronomical data online, looking for moving objects that automated algorithms might have missed. The human eye and brain are remarkably good at pattern recognition, sometimes spotting subtle movements or anomalies that sophisticated computer programs overlook. The profound implications. Planet 9's discovery would represent more than just finding a new planet. It would fundamentally change our understanding of solar system formation and evolution. If such a massive planet exists in our solar system, it represents a fundamental gap in our knowledge of our cosmic neighborhood. More importantly, Planet 9's existence would mean that our solar system is far more dynamic and potentially unstable than we've assumed. The gravitational influence of such a massive world even at vast distances, would affect virtually everything in the outer solar system over long time periods. Comet orbits, asteroid trajectories, even the tilt of the solar system itself could all be influenced by this hidden giant. The discovery would also have implications for planetary science beyond our solar system. Our solar system notably lacks super-Earths, planets more massive than Earth but smaller than Neptune, making it somewhat unusual among known planetary systems. Planet Nine's discovery would place our solar system squarely in the mainstream of planetary architectures observed elsewhere in the galaxy. But perhaps the most significant implication would be the humbling realization that we don't know our own cosmic neighborhood as well as we thought. After decades of assuming that the major planets had all been discovered, finding a world 10 times more massive than Earth would be profoundly unsettling. Ancient warnings. Modern science, as we stand at this threshold of potential discovery, we're forced to confront an uncomfortable truth about our place in the cosmos. The stable, predictable solar system we've assumed we live in might be an illusion created by our brief existence on geological timescales. The real solar system might be far more dynamic and dangerous than we've realized. The ancient Sumerians spoke of Nibiru as a harbinger of change, a cosmic force that brought both destruction and renewal. They described it as a world of crossing, a planet whose orbit intersected with the paths of other celestial bodies, creating periods of upheaval and transformation. Modern astronomers don't use such poetic language, but their calculations paint a remarkably similar picture. If Planet X exists, its periodic approach would represent one of the most significant gravitational influences in our solar system's history. Every few thousand years, this massive world would sweep through the outer planetary regions, its gravity stirring up the cosmic debris like a giant hand, disturbing a carefully balanced mobile. Whether Planet X lurks in the outer reaches or other secrets guard the edge of our solar system, the search continues with increasing intensity and sophistication. New telescopes coming online will be even more sensitive than current instruments. Machine learning algorithms are being developed specifically for Planet 9 searches, capable of processing astronomical datasets far larger than human analysts could handle. The truth is out there, hidden among the stars, waiting for human ingenuity and persistence to bring it into the light. When that moment comes, when we finally confirm or rule out Planet Nine's existence, we'll take another crucial step in understanding the cosmic forces that shape our world. Asterisk in the vast darkness beyond Neptune. Mysteries await discovery. The search continues for answers that could reshape our understanding of our place in the cosmos. The universe keeps its secrets well, but human curiosity and scientific determination have a way of eventually illuminating even the darkest corners of space. Asterisk.